It's my real pleasure to introduce Romain Ragonnet. Have I said it correctly? Thank you. I tried. So Romain very agreeably allowed us to make him the very first presenter for 2025's reinstatement of this journal club. He is an NHMRC early emerging leader. He's got extensive experience with TB modeling. I had the great pleasure of going to a meeting with him on Thursday and Friday last week. So I got to know him a little bit better. So he came across a while ago. Was it 2018, 2019, Romain?
You mean when I moved to Melbourne?
Melbourne.
2015, I think. Yeah.
2015, that's right. Yeah. He was supposed to come for 6 months and then got stuck because he loved Melbourne so much.
That's right. Yeah.
He started a PhD at the University of Melbourne, and he is now a senior research fellow at the EPI modelling unit at Monash University with James Trower. He's led multiple modelling projects and advised on policy in TB control across the Asia-Pacific region. He's contributed modelling to guide governments on the pandemic response to COVID-19, and he's built a wide interdisciplinary network involving infectious disease physicians, respiratory physicians, medical ethicists, biostatisticians, and those involved in mathematical optimization as well. And outside of work, he's a dad of 2 young children, and he loves spending time in the ocean, kite surfing, and exploring new food experiences. So it's my real pleasure to have Romain start today's Journal Club. Thank you.
Thank you so much, Gail, for this introduction. We'll try to share this laptop. Yeah, okay. It seems to be working. Okay, great. So that's great. I don't even have to introduce myself. Thank you very much, Gail. That was a great introduction. And you did pronounce my name perfectly well. So well done. This is not very common from English speakers. So well done. So I'm very happy to be presenting on this article or preprint today. Thank you for the invitation. I also want to thank Andrew and Nashita who coordinated this meeting. So this is a preprint I came across recently about modeling the impact of active case finding for tuberculosis. And this is very much my number one interest at the moment. I'm planning to look at active case finding and how we can best model this intervention and how we can use this to assist policy making. I'm planning to look at this for the next few years. So that's a really important paper for me, and also a very important question about the role played by the infection dynamics when we are actually trying to model the impact of case finding. And in this particular paper, they really focus on the potential clearance of infection, because in previous modeling studies, most of the time we assume that once people are infected, they have this lifelong risk of infection. We do generally assume that there is a higher risk of progression towards active tuberculosis in the early stages of infection. And then we have a reduced risk of progression at a later stage. So that's kind of the most commonly used assumption. But we don't really see infection clearance captured explicitly very often. So I think that's an interesting topic. And I guess even before we dive into the paper and before we look at the methods or anything like that, I think there's probably some intuition we can actually think about in terms of the interplay between the effect of active case finding and the assumptions we make around the dynamics of TB infection. And I think if you think about active case finding in terms of only focusing on active TB cases, and we just forget about preventive treatment for now, but just active case finding as focusing on active disease. Obviously, if you try to estimate the impacts of detecting more people with active TB, your estimates are going to be affected by the assumption that you make about people who are currently infected but don't have this active form of the disease. And most importantly, about the risk of progression towards active TB for these individuals. So that's what this paper is about. And that's a paper written by Theresa Rickman, who works with David Dowdy and Emily Kendall at Johns Hopkins University. So once again, it's a preprint, so it hasn't been published yet, but I think it's a very topical paper, so I thought it was a good occasion to discuss it. So this is what I'm planning to do for this session today. I'm very happy to make it interactive, so just feel free to interrupt me or ask questions at any point. But what I'm trying to do today is not only going through the paper and trying to find out about the main findings and the key messages, but I guess when I look at the audience today, I think there's actually not so many modelers or mathematicians or even statisticians around. Looks like most people are maybe clinicians or have other expertise, but not necessarily a modeling expertise. So what I'm trying to cover today is more generally how we can actually try to decode or understand a modeling paper when we are not a mathematician or a modeler. And of course, we are going to use this paper as a support for this. So that's basically the plan for today. But again, I'm very flexible and just feel free to jump in anytime. So let's have a look at the paper maybe first. Okay, so maybe a few key pieces of information from the abstract. So what they are trying to do here is basically comparing two different conceptual approaches to how we capture TB infection. And they are doing this by building two separate models, each reflecting a separate assumption. So the first one that is highlighted here in yellow is we are going to assume that there is a lifelong risk of progression from latent infection to active TB. And they will call this model conventional because that's basically what's been used most of the time before. And then they will compare this with their clearance model, which is the one that actually assumes that some individuals clear their infections. So at some point, they just don't have this infection in their body at all. And when comparing these two models, what they are also going to do is project the impact of community-wide screening or active case finding and see whether there's any difference between those two models. So I guess in terms of background, a few interesting points from the introduction section. The first one is to say that, there seems to be some evidence that suggests clearance of MTB infection. And that's something that's been discussed before and also documented multiple times in terms of the ability of reversion, for example, where people can test positive to TST or IGRA tests, but then these tests might be negative at a later stage. I think it's still unclear what this actually means in terms of infection status and risk of future disease, but at least there seems to be some evidence that this infection stage is very much dynamic. It's not something that is just, you're infected and you are that given risk and you're going to have that risk for your entire life. It does seem to be more about an evolving phase that could be progressing one way or the other. I think we did discuss the importance of these dynamics for active case finding. So that paper is actually looking at that. So what I'm planning to do is first looking at this paper very quickly and just highlighting the main findings. Then we will move on to discussing how we can actually interpret a modeling paper, even if we are not modelers. And while we are doing this, we are actually going to come back to some of the findings that might be a bit more specific and maybe more technical. But maybe for the first read, we can just focus on a very big, like the main findings. And one of them was in terms of comparing the two models regarding their ability to fit the data. So when we say fit the data, it's about the calibration targets that the authors selected. And these are basically observations from the real world that they actually want their model to match or to capture. So they want their model to look as closely as possible to look like these observations. And that's one way to assess whether a model is better than another one, is to actually compare their ability to replicate the observed data. And what they seem to find here is that the model with clearance is actually able to capture the observations a little bit better than the other model. We'll come back to this in more detail later, but I think that's an important finding to start with. Another thing they compare between these two models is the fraction of infections that was recently acquired as opposed to remote infections. And there seems to be a difference between the two models once again. So with the model that includes clearance in their model structure, the acquired infection, the infection that were recently acquired is actually more prevalent. There's actually more of this type of infection as opposed to remote infections. And that kind of makes sense if you think about it. Like if you think about TB infection as a sequence of two stages with kind of early stage and late stage. And what they assume in this particular article for infection clearance is that clearance only applies to the late stage of infection. So what they are saying is that basically with infection, you have to go through these two stages. But if you have clearance that kind of drains the late stage compartment, then it kind of makes sense that the relative size of the early infection stage is going to be greater. So that's one thing they highlight here. And then, something that we've mentioned very briefly so far is in terms of the impact of active case finding. So what they are modeling here is waves of mass screening in the population, and they mention about 75% coverage for the population, and they would repeat these waves every 2 years. And they also do this under two different assumptions. First, they are actually looking at doing ACF with TPT provision. So TPT is tuberculosis preventive treatment. So they're actually looking at both with and without TPT included in the ACF activities. And they, of course, repeat those analyses for both models, both the clearance model and the conventional model. And what they found was, and I think the numbers are, that's probably what I should have highlighted here. So what they do is then they project the epidemic for 10 years following the start of the interventions. And they compare the impact of ACF for the clearance model against the conventional model. And I think that's probably the most important finding for this paper, is that the impact of ACF was found to be greater under the clearance model assumption. You can see here about a 26% reduction in incidence compared to 11% only for the conventional model. So that's their main finding that is also highlighted with this figure. So here what they do is they compare the model projections between the conventional model and clearance model for the impact of ACF intervention. The red line is ACF without preventive treatment. Orange line is with preventive treatment. And all of this is compared to a kind of business as usual scenario where there is no active case finding implemented. Those figures just reflect the same finding that I highlighted in the text. But another finding they have here is that when you do include preventive treatment, so now we're looking at the orange lines, you basically have no difference between the two assumptions. And I think there was a question from Gail. You are raising your hand.
Sorry, I just wanted to check, Romain, with regards to, so in the conventional model, I was just checking whether clearance meant that they were given TPT to clear their infection, or whether it meant they self-cleared.
When they give TPT, they just assume that people move from an infected state to a recovered state.
Yeah.
The clearance model is incorporating spontaneous clearance.
Yes, it is. And I will come back to this when we look at the actual model structure and the assumption associated with this.
Okay.
Yes.
Thank you.
So that's probably the main finding is probably summarized with this figure here. And I think what's interesting is that, even when I started and before we start looking at the paper, I said, well, there's probably some kind of intuition behind this question. And we can kind of guess what's going to happen in terms of which way the predictions are going to go when we compare those two models. But what's interesting with modeling, I guess, is that you can then quantify how much of a difference it makes. And that's what we see here. Just one thing I want to highlight is the amount of uncertainty for all of those projections. And that's something we are going to cover next as well, to see where this uncertainty comes from and how it's being addressed with this analysis. So I would suggest that we move on to the next phase, which is about, how do you actually interpret this modeling when you're not a modeler, and how you look for the key information in terms of the underlying assumptions that are being made. And, one example is the question that Gail just asked. How do we actually detect these kind of things in the model and in the description of the methods? So maybe we can move on to this unless there's any question from anyone.
Thanks for that overview. I had a question about the models which you have described, but after latent TB treatment, also active TB treatment, reinfection with TB is a possibility. Is it accounted for in many traditional models? How could that be accounted for?
Yeah, it is. So it is usually accounted for. In this particular paper, it is accounted for, and we are going to cover this in the next few slides.
Yep. Okay.
And that's a very important point because that's a very big unknown. I think one of the big unknowns of TB epidemiology is we know that there is a risk of reinfection, but actually quantifying this risk relative to infection-naive individuals is still quite unclear. So that's a really important point of discussion.
Cool. Thank you.
And as well as after clearance, I suppose, even during latency.
Even during latency, yes. Okay, so and actually we're probably going to discuss this right now, among other things, but that's I think the most important thing to understand if you want to have a great overview of the main assumptions that are being made and how TB disease is captured and how TB infection is captured by the modelers. And this is a representation of the dynamic model that is being used by the authors. And to think about this type of model very simply, it's all about having a population that is stratified by different, that is stratified according to infection status. So you have people with the uninfected status, so they never had any TB infection. Then you have people with infection, but not active disease. So that's the brown boxes here. And you can see that they are actually representing recent infection and remote infection. So that's something that we've discussed earlier. So as you get infected, you move to these compartments in which you stay for a given amount of time, and then you move on to remote infection, provided that you have not progressed to active disease yet. And you can see that there's lots of back and forth transitions, but this is because, for example, if people have experienced recent infection and are now in the remote infection category, they might actually be reinfected. And if they are reinfected, then they move back to this recent infection category. So that's probably one of the parameters of these models that is quite uncertain, is what's the risk of reinfection for people who are currently infected. After infection, you may progress to active disease. And once again, we have two different categories to represent this active disease category. You have the pre-care seeking category. So that's people who have active TB, but have not been detected yet. So they can't be provided with active TB treatment. And then they explicitly capture people who are actually seeking care and have the opportunity to be treated for TB. You can see here we have the recovered state, and you actually have multiple pathways to recovery. So one of them is maybe the first pathway that comes to people's mind when they think about TB recovery, and that's probably through treatment. So you have TB, you're detected, you get treated, and that's actually the pathway that you can see. And sorry, I'm just struggling to show my cursor here. Let's try with this. Yes, very better. So that's this pathway here. So that's recovery induced by active TB treatment. But there's also people who recover without any treatment. So that's the self-resolution pathway. And what they add here as well is the active case finding treatment. So it's probably similar to this pathway here, but this transition will only be relevant to the scenario where we actually have active case finding implemented. We have TPT. So that's a transition from the latent infection categories to the recovered state. And to answer the previous question, you can see there's actually a transition back from the recovered compartment back to the infection compartments. So that's the one that's about reinfection for people who have been either treated for active TB or treated for latent infection or have cleared their disease spontaneously. And the key transition that is actually highlighted in this paper is the blue transition here. So that's for infection clearance. That's about people moving from the remote infection stage to the recovered stage. From the recovered stage, it's important to to highlight that there's actually no risk of progression back to the active TB compartment. So that means that we assume that once people have cleared infection, they have no risk of progression to active TB anymore, unless they get reinfected again and they go back to the full cycle of infection. So I think that covers pretty much the main structure for the model, the main transitions. Gail, you have a question?
Yeah, I was just curious. Did the modelers not feel that someone who has recently acquired infection wouldn't be able to clear the infection, which is why they don't also have a blue dotted line from recent infection to recovered?
Yeah, I think that's probably what they assume is that when you're with these two stages, recent infection versus remote infection, there's actually two things that are captured. So one is a temporal thing. It's about saying, well, you start in this recent infection compartment. And I believe in this paper, they assume an average duration of 2 years for this recent infection. So I think that's probably answering a question I've just seen in the chat. So for about 2 years, they stay in this compartment, then they move to the remote infection compartment. So that means a later stage. But it's not only about temporal dynamics. It's also about the level of risk there is from these two compartments. So for example, here, recent infection, you have a much higher risk of progression to active TB compared to the remote infection one. So I guess what the authors are assuming is that because you're at higher risk of progression, it's probably a stage of your infection where you may not be able to clear the infection completely. So it's probably a reasonable assumption to make to say that we're only going to look at clearance from this compartment, the remote infection compartment.
The reason I asked this specifically is because, I'm interested in biomarker discovery, and one of that includes PET-CT and then macaque models. And in those models, those animal models, it is apparent that some animals spontaneously clear infection. So they have recently acquired infection that they clear of their own accord, using PET-CT data, then followed by obtaining histological samples and culture that shows that they spontaneously clear without treatment. So I guess that, with that in mind, I'm just wondering whether the model perhaps, it's wonderful that they are now considering infection clearance as part of it, but it may also be possible that infection clears earlier than the 2-year period of time. So in that recent infection category, yeah.
Yeah, right. And I think that's right. And one thing to mention, and it might be getting a bit technical, but when we say this compartment represents, in average, the first 2 years of infection, that's an average. But the reality when you're using these models is that the time spent in this compartment is actually distributed. It's actually following a statistical distribution, and that's an exponential distribution in that case. So that means even if you say that's in average 2 years, you still allow for people to progress immediately to the later stage compartment. So you might actually you might be capturing some of these phenomena that you were describing.
Yeah, I understand what you mean. The recent infection being 2 years actually might mean that in the model, because of the mathematical principles, it might be that someone stayed in the recent infection phase only for a month before progressing to the remote infection
exactly. There would
subsequently.
There will be those staying for a month, so there will be those staying for 10 years. It's the statistical distribution with a mean equal to 2 years. Yeah.
Cool. So, for example, you could plot out the distribution of when people arrive in recovered, given that they were infected at, say, time 0, and that would give you a sort of a non-zero estimate from not long after infection, I think.
Yeah, that's right. Yeah.
Thanks.
We'll have a quick look at the chat to see if there was any question related to the model structure.
There was, I think.
Okay, so what do we mean by remote infection? I think that's been covered now. Yeah, so comment from Katie about the assumption that there is no reversion in the first 2 years. Yeah, again, I think we've just covered that. It's not exactly what they assume, because there is, again, this time distribution that is a continuous distribution.
I'd like to ask...
Yeah.
Sorry, Romain, just one of the things I think I'm quite curious about is this concept of recent infection versus remote infection. And particularly because I remember speaking with a lab scientist who works in the HIV space, was talking about there appeared to be some information that suggested that looking at HIV antibodies, you could tell how long ago they had been infected. And we don't have any such tool in TB, for example. We don't have any assay or otherwise that tells us even an estimate of when someone has been infected. But I guess, looking at something like this, what would be useful from a modeling perspective if you had a biomarker that would be able to inform us of when recent infection occurred or when remote infection occurred or when clearance has occurred? Which of those would be, if you had to be able to pick one, what would be of value?
I don't know. I think the question is also for like TB control in general, like not only for modeling, and maybe most importantly for TB control, and then we could look at this with modeling. But I think obviously what would be fantastic is to actually know what it means when you have people testing positive. Like you have someone testing positive with TST or interferon, you still don't know what that means in terms of risk of progression. And I think that's probably the most important, is to actually know the risk of progression. Yeah, because it may not matter too much to know how long ago they've been infected. It's more about the risk of progression. And again, I think that's very much of a dynamic, progressive stage. And, like all we're seeing here with those big boxes and categories, this is just a model. This is just a conceptual way of thinking. And we all know that it's actually a continuous spectrum. Like, we have recent infection, remote infection, active disease. We could easily argue that it's actually just one big state, and there's a continuum in terms of symptoms, in terms of what test would turn on being positive. It's very much what modelers are proposing here is just a simplified way of representing or capturing this complexity. And because it's been simplified, then you might be able to think about this process more simply, and you might be able to find interesting conclusions. But it's always good to keep in mind that this is actually not the reality. We know that it's just one way to simplify things.
Yeah. Thank you. I needed that reminder.
And I think the big question they're asking is, we know that models are simple in a way. They're very, very simplistic representation of the real world. And what they are asking here is it actually worth adding some complexity to this simple model? And in that particular example, it's about infection clearance. And they actually argue that it is probably worth doing.
I find it quite fascinating that, we certainly in clinical care, at least in the clinic I practice in, we can't consider infection clearance. We assume that once a person is infected, or occasionally we do, we assume that they're infected for life and remain able to reactivate at any point in time, unless they've received latent or active TB treatment. That's the only point in time we say, they've recovered. But then there's always a consideration that someone might become reinfected if they've traveled back to an endemic area. So it is really nice to see that they're building infection clearance into these mathematical models and how it fits the data better as a consequence. And maybe we should also be considering that in our clinical practice and what it means for when we're looking to see what the real risks are to people. But I think that's a bit difficult for clinicians because we really just don't have the tools to be able to tell us whether someone remains infected or has cleared the infection. That's the real problem.
Yes. Is this what Katie might have asked in the chat? How do these compartments map to?
Yeah, I was about to cover this because that's a very important point for this paper. So how do we match these compartments or these different infection statuses with like TST or any immunoreactivity test? So what they assume in this particular analysis is that only these two categories would test positive to a TST, for example. So once people have cleared, they are in this recovered compartment where they are assumed to test negative. So that's one assumption to keep in mind, especially because they actually do some comparison with their estimates of TST positivity rates against data from the National Prevalence Survey. And they do map these two compartments to the data. So they are actually assuming that after clearance, you are testing negative. That's a very important assumption. Another thing related to this is because these individuals move to the recovered compartment after clearance, yes, they can get reinfected, but we'll have a look at the parameters next. The risk of reinfection from the recovered compartment is actually lower compared to the risk of infection from infection-naive individuals. So that what they are saying is basically once people clear infection, they have no risk of progression. They would test negative to any immunoreactivity test. But also, what they're still assuming is that they retain some sort of protection, some sort of partial immunity against reinfection. Again, that's an assumption. I have no idea whether that is accurate. And I would think there's a lot of uncertainty around this point. Do people who have cleared infection retain some sort of partial immunity against reinfection? I don't know whether that's true or not, but I think that's an assumption that's good to keep in mind as you interpret the findings. And in that case, I think it's also good to think about the alternative assumption, which would be instead of people moving to the recovered compartment, they could actually move to the non-infected compartments. And then you have actually a population that has the same risk of infection as initially before any infection. And I think that would be quite interesting to look at this question, like comparing these two assumptions, because there's probably so much uncertainty about this, remaining amount of immunity against reinfection after clearance.
Can I just say something very quickly to that point? In fact, I think there are data to suggest that people who are at risk of primary infection are at actually increased risk of reinfection, as opposed to it conferring some protection. There are some vulnerabilities in either their social standing, their social structures, or their immune function that may actually predispose them to repeated infection rather than the other way around. Yeah,
exactly. And you can capture this with this kind of model. You need to make it a little bit more complicated. One way to do it would be to replicate this model for different categories of the population. And you might have a high-risk group and a low-risk group. And then you might be able to capture these phenomena that you were describing, Dave.
Yeah, I mean, my understanding is that people who have had TB previously are at increased risk of reinfection, but that we don't really understand what the mechanism for that is, whether it's individual level susceptibility or whether it's just sort of the exposures they've had. But I haven't looked at that evidence in a little while.
Any other question about the model structure? No? Okay, so I'd like to move on to now how how do we interpret the findings, and how do we identify the main assumptions that are, and I think we've identified a few already, and sometimes they are not necessarily written in text. They might be just looking at the structure and looking both at the model structure and the parameter values. That's actually what's going to tell you the assumptions. So I'm going to move on to the next slide, because that's actually very much how I think about a TB model, and probably any infectious disease model in general. It's actually a balloon animal, in the way that it's a very highly flexible object. You see this model, which looks quite complex with all of these transitions. What you have to keep in mind is that it's actually a very flexible object, because it's all governed by these transitions that are all associated with parameters. And if you change the value of a parameter, then you might have a situation that is completely different. We were discussing the risk of reinfection just before, and you can see you have these reinfection flows. If you increase the risk of reinfection related to the original risk of infection, you might have an epidemiological situation that is completely different. So that's why you have to think about this model as something that is quite flexible, which is good in a way, provided that you constrain your model using data, using observations, using evidence. So in a way, you can think about a model as this balloon animal, maybe building the model and coding the model is maybe only equivalent to inflating the balloon. And then if you want this model to look like something realistic, then you have to make those twists. And the way I think about it is that every time you make a twist is equivalent to having some data that you are using to inform your model and to inform your parameter values. So we're going to see how this is being done, but just keep that in mind, is that a model with no data will have very limited value. The more data you add, the more realistic you make it. And then you have to make sure that your model is capturing the realities. So how this is usually being done. So think about this modeling framework. Very simple. You have these input parameters that are associated with the transitions in the model structure. You have your model, and then that generates your model outputs, including TB incidence, mortality, prevalence estimates. And the way you can use the data first is to inform your input parameters directly. So, for example, do we know about the annual rate of TB mortality in people who have active TB? And that could be one example of input parameter, and maybe we have some evidence that can inform this one. Another way to use the data is to compare the model outputs with evidence that you get from the real world. So one example is TB prevalence, and that's probably one of the best data that's currently available for TB. If you have access to data from a prevalence survey, then you have this estimate of active TB prevalence that you can match. You can actually map with your model output on TB prevalence. And when you do this process, you can actually check that you have a good match here. And if you don't, that means, well, probably we need to adjust those input parameters. So that's basically two ways of using the data. One as model inputs, another one as comparator against the model outputs. And what they do here is they do this exact process, combining these two ways of using the data within a single framework, and that is actually very commonly used in TB modeling. So using a Bayesian sampling approach. So what they do in this context is, for each parameter that you want to calibrate, and when we say we're calibrating a parameter, that means we don't have a fixed value for this parameter. We are going to allow this parameter to move around. And you'll see that there's some constraints imposed on these parameters, but they are still allowed to move around. And when you do this, for each calibrated parameter, you specify your prior knowledge. So that's, what do I know about this specific parameter before doing my analysis. And that is usually driven by previous evidence or expert opinion. But this is represented by statistical distributions. One example is a uniform distribution when you say, oh, this parameter value could be anything between A and B, and I don't have any preferential knowledge for any value between A and B. So you just say it's between those bounds, and that's all I know about it. And this kind of prior knowledge could be more restricted in some cases. So you could still have a uniform distribution with a range which is more narrow. So that means you're actually more restricted in terms of the values that this parameter can take. But what you can also do is to say, well, yes, I know it's between A and B, but it's actually more likely to be around a specific value. And here for this example, I just said, well, that's just the midpoint in that interval. But you could have any statistical distribution. You could have a normal distribution. You could have anything you want to represent your prior knowledge. Once you've done that for your input parameters that are being calibrated, you also define your calibration targets. And that's the data that is used for comparison against your model outputs. So, for example, TB prevalence. Then this kind of sampling approach is using algorithms that involve sampling a very large number of parameter sets. And for each of these parameter sets, we are going to assess whether they are plausible or not. And this is done using two components. One is whether it's consistent with your prior knowledge. So, for example, if you're sampling a parameter value that is outside of this range, it's going to be rejected systematically because it's not consistent with your prior knowledge. And then it's also going to assess the goodness of fit between model outputs and your data. These two components are combined together, and that gives you kind of a combined score that tells you whether a parameter set is good or not. And then the algorithm is going to accept or reject based on that score. At the end of the calibration task, you have access to a sample, a very, very large sample of accepted parameter sets. And that's only this sample that's going to be used for your analysis. So you can see that you start from your prior knowledge, and then through this calibration process, you end up with, I would say, a filtered set of points or parameter sets that are actually suitable for your problem and that you are going to use for the analysis. So that's a very commonly used approach. And what I'm explaining here as the main steps is a very rough approach. And then there's, of course, many different flavors to these types of algorithms. There's very different ways to define your priors. There's different ways to sample those parameter sets. But that's always kind of the same philosophy. So for this particular paper, we can look at the input parameters and the values that are used. And you can see it's actually a mix of fixed parameters. So for example, here, some parameters driving the interventions, they are all fixed values. And the prior parameter distributions, that is where you actually allow these parameters to move around and you're calibrating those parameters. So for example, you can see the progression rates, both from the early and late stage of infection. They are calibrated. And then you can see there's a range associated with each of these parameters. And for each parameter, they use a uniform distribution as a prior. So that's your prior distribution represented here for each parameter. One example of insight you can get from this type of table. I'm getting back to this risk of reinfection. And you can see it's actually listed here, relative risk of reinfection. So that's compared to the infection-naive population. And you can see this is actually allowed to vary between 0 and 1. So it can do anything, but what we're actually assuming is that it's never going to be higher than 1. So we are assuming that the recovered population has a reduced risk of infection compared to the infection-naive population. Any comments in the chat?
Don't know whether they should have been using all those parameters by Ragonnet yet. How later?
Yeah, I don't know how it is.
I have another question, if I may ask. Do you think that it should be a uniform distribution? For example, I was just thinking, we know that with your risk of activation of disease is earliest the closest you are to infection. So that's not really, if you were looking at your early progression rate isn't a normal distribution. The first month post when you've inhaled the TB is probably at the highest risk, so it shouldn't be normally distributed, if I've understood this.
Yeah, that's exactly right. So, there is some previous knowledge about those risks. So the authors could potentially have used more informative prior distributions. Now, what they've done instead is they're using kind of what we call a flat prior knowledge, just a uniform distribution. But instead of using an informative prior, they actually use targets for calibration. And we'll just show the next slide here. The calibration targets, so these are the outputs they are trying to match between the model and the real world. There's actually a few targets that could be constraining the risk of progression. And you can see here, they are using data on cumulative progression after 2 years and also after 10 years. So by using this data, you're actually constraining your progression parameters. So in a way that becomes kind of equivalent. It's either you use this data as inputs to design your prior distributions. But then if you do this for your priors, you're not supposed to use it for your calibration targets. Or you do the other way around, and that's what the authors are doing now, is they say, well, let's use this information as calibration targets, but to avoid using this data twice, I will just use a flat and informative prior.
I think, what I wanted to highlight here is just, pay attention to these numbers. Like, I know these are big tables. I know there's a lot of information. This is actually where most of the assumptions are kind of hidden. They're not hidden because they are actually there, but you just have to know that this is where you have to look. Understand what's being done with those numbers. You allow the parameters to move around, but it's not actually completely unconstrained because you have those calibration targets that will make sure that you still have realistic values. And I think, there were a few points I wanted to make, but I think we're running out of time. So do feel free to get in touch by email if you have any question or if you want to keep discussing this particular paper or any other TB modeling analysis.